myself and my other collaborators, Bart and Keith, have been working for 4 years on building an informatics domain model. And that has led to us developing a core data ontology for computational systems. So this talk introduces a core data ontology and the informatics domain model, which shift computational systems from traditional node-centric architectures to a data-centric paradigm. So I'll be presenting this probably by myself. I'm really the architect behind the informatics domain model. And Bart from the University of Toronto was in charge of building the core data ontology. So if he dials in, I'll pass over to him. If not, then I'll talk through that as well. But the session explores how data can be categorized into 4 modalities: objects, events, concepts, and actions. And this quadrimodal structure enhances data security, semantic interoperability, and scalability across distributed ecosystems. The core data ontology is then a comprehensive framework that supports AI development, role-based access control, and multimodal data management, prioritizing data security, provenance, and auditability. So we can discuss this also in regarding applications in AI, robotics, and legal compliance, while outlining further directions for decentralized and interoperable data ecosystems. So I'll start with this slide. This was really kind of the start of the whole journey. I really started this journey when talking to the decentralized identity folks, experts in self-sovereign identity, and I just realized that semantics wasn't really getting a fair shake of the stick. Everything was, in that community, they were really talking about authentication of entered values into a system without concentrating too much on the semantics and the meaning of the information that was being entered. So it started with a kind of an inputs versus semantics kind of model, and then through that development, then we kind of started developing this data-centric model. But in short, what it enables, a node-centric system design centralizes control, securing specific locations or platforms, often leading to isolated data silos and restricted data flow between those controlled nodes. Whereas if you put all the security around the data exchange packet itself, you can create a data-centric system, which is designed so you secure the data itself, and that enables interoperability and the seamless sharing of data across systems, thus eliminating the need for data silos. So out of the 4 domains, actually, I'll go to this slide here so you can kind of see the model itself. This is where we distinguish between structure, causality, knowledge, and intelligence. So objects, events, concepts, and actions, or another way to look at it as data capture, data entry, data access, and data exchange. Then just having through these kind of 4 domains, you have all of the domains to ensure that any exchange data across the system is accurate. What do we mean by accurate? So I'll quickly go through this. Morphological structure, object schemas define how textual attributes contribute to the morphological structure of systemic variables, data structures, functions, and methods. Kinematical causality. So you can kind of think of kinematics in the mechanics world as being dynamics versus kinematics. So dynamics is more on the action side, kinematics is on the event side. So event records provide tractional fields of evidence for tracing kinematical causality, schematic event sequences, and relationships between interconnected vertices, supporting the study of motion and causal connections. Epistemological knowledge, which is really in the ontological space. So this is concept frames. So they define how nodal entities and contextual terms and relationships contribute to the epistemological knowledge of epistemic concepts or abstract ideas. And then finally is the action domain. So you can think of that as computer processing any processes in the system. So this is action packets contain factual information for systematic actioning agents to process dynamical intelligence for value-based lifecycle operations. A couple of the cross-domain correlations in here are important just to have a look at. So one is semantics. So semantics consists of both objects and concepts. So on objects, it's about morphological structure, and then concepts is about epistemological knowledge. So those two domains together, they make up semantics, and together those words are consensual scheme. So if you look at the definition of scheme here, you'll see it's a large-scale systematic plan or arrangement for attaining a particular object or putting a particular idea into effect. And actually, in the Oxford Dictionary, concept is defined as an abstract idea. So you'll see that's beautifully defined here for really what semantics is. It's about schemes. Whereas on the other cross domain here, between actions and events, this is the mechanics. So here you can talk about the causalities, so the kinematical causality, which is really about how you track events according to movement. So in a system, obviously, if you can trace the events, then it becomes verifiable and with full provenance. And then on the other side, on the action side, is more about the dynamics. So that's the only domain that brings any active elements into the system. So it's basically semantics on one side and mechanics as the other cross correlation. And in mechanics, it's called reason. So if you look at here, reason, a cause, explanation, or justification for an action or an event. So again, it's beautifully defined in the Oxford Dictionary. And I found this wonderful quote from an ancient Greek philosopher: "It is a habit of mankind to entrust to careless hope what they long for, and to use sovereign reason to thrust aside what they do not fancy." So they've been talking about this since 400 BC. And with a data-centric model, you can start to model these ancient concepts that we already know about. I've put some academic references into the paper for morphological semantics, kinematical mechanics, epistemological semantics, and dynamical mechanics, so people can go and check those out in their own time. And what this really led to was the core data ontology. So in some of you see I've done the cross correlations of scheme and reason, but when we did the correlations for some of the other domains, we came a cause and effect, methods, and goals. And through this kind of patterning, we could start to build a core data ontology. Again, I've got all the definitions for what those 6 correlations are. In the paper, there's actually a link to this deck, so you can kind of see it all there. But again, I've tried to keep everything a reference to the Oxford Dictionary in those definitions. So these are all really about the functional correlations that describe the practical cause and effect relationships between objects, concepts, actions, and events in the domain. These correlations focus on how elements interact to achieve specific outcomes or purposes. So, and I guess for you ontologists out there, you'd be interested in the ontology. So we were able to kind of keep a closed ontology specifically to model the correlations of the informatics domain model. And it kind of looks a bit like this. So in here, you've got, all of the relationships between all of those nodal entities within the ontology. Again, you can take a look at the graph here in your own time, but as you'll see, it really is a beautifully knit and tight ontology. So I don't think I've got Bart on the call. Let me just have a look if he's on the call. I don't think he is, though. No, he's not on the call. So, Bart's really the guy that built the core data ontology. So I can definitely answer some of the questions regarding the ontology, but really my expertise is more in the domain modeling of the informatics domain model. So that's everything I had for this presentation. Does anybody have any questions? I've got my email here at the end of the presentation. If you send an email there, you can